So in this video, we're going to try to take a look at some of the consequences that follow from the definition of a limit that we established in the last several videos. Now, we'll start here with probably one of our most important theorems for this particular section in evaluating limits. And throughout the remaining videos, what you'll see is we'll generate additional theorems, or additional tools, if you will, to help us try to answer questions like the ones we'll start seeing here in example number 4 and 5. Here's what our first theorem says. If it's the case that we have the limit of a regular old function, like a function we would see in Calc 1, not a sequence, but just a regular old function, and if we know what happens on this function as x goes off to infinity, let's say this equals L, and we also know that f, when I plug in n, is equivalent to a when I plug in n. I kind of imagine this is like f is a matching function for this sequence. Or if I was to think about this pictorially, maybe like down here, what this says is that if I have a function, let's say my function goes like this, then along that function, if I plug in values of like 1 and 2 and 3 and so on, I kind of see that my sequence is kind of dots along the path of that function. So it's a matching function for my sequence. Well, again, if I know what the limit is of that sequence, then it's probably almost pretty obvious to see what the result of this theorem is going to be. Well, if I have this, then if I know where the function is going and my dots are all on the function, then the limit for my sequence should also be L. Wherever the function goes, the sequence goes. This is a really useful tool. So take a look down here at how we can use this with example number 4. Use the above theorem to show that if my sequence is n over n plus 1, I could show that the limit is indeed 1. Now again, to do this, I'll use the above theorem, which means I need to create an f of x function. It's very important here in Chapter 5 that we get in the habit of writing out our explanations using nice, complete sentences. So pay careful attention to what I'm doing here. Notice that first I'm establishing what my function is. I'm not just writing it down. I'm saying, how about we let f of x be equal to this? We see that I can easily calculate a limit of our f of x function. The limit of this function is going to be the limit of x over x plus 1, and I could think about how I wish to evaluate that. Now there's lots of different ways to do it, but one way that would be really easy here is to enact L'Hopital's rule. Notice I do have infinity over infinity, and so it's possible to use L'Hopital's rule here. And this, of course, tells me that if I take the derivative of the top and the derivative of the bottom, this limit should match the answer to this limit. So this is really just the limit of 1, and the limit of 1 is 1. Notice I haven't yet answered the question. I can say, though, that since the limit of f of x as x approaches infinity was equal to 1, then I know that the limit of a sub n as n approaches infinity is also equal to 1. And usually at the end of an argument in mathematics, you put something like a little square. If you're really awesome, you try to shade it in. It's just a cool thing to do. Sometimes you'll also see people write something like QED. You may have seen that before. Now, we're going to go ahead and continue to try to use this sort of notation as well as the way that we write arguments when we look here at example number 5. So here in example 5, I want you to try to go ahead and pause the video to see if you can determine what the limit of this sequence would actually be. Now again, you can use the above theorem and the general kind of structure of how we wrote out our argument up above to try to determine the answer to this question. Go ahead, pause the video, see what you come up with, and of course, when you've attempted this, you can hit unpause to see me work through the solution. Okay, so what I would actually do here is to say, how about we let f of x, again, be equal to the natural log of x over x? Well then, I can easily say that we see that if I was to do the limit of f of x as x approaches infinity. That's the same thing as really saying that I'm taking the limit of natural log of x over x. Conveniently again, notice I need to check this. L'Hopital's rule does apply. Top of the fraction is going towards infinity, bottom of the fraction is going towards infinity, and so it's possible to use L'Hopital's rule. This then means that I can go ahead, when I take the derivative of the top, I get 1 over x, and on the bottom I get 1. But really this is then just a limit of 1 over x, and as x goes off to infinity, this has an answer of 0. I haven't answered the question, but I can easily go ahead and just write down my conclusion. I can say, since the limit of f of x as x approached infinity was equal to 0, then we know that the limit of a sub n, well, wait a minute, that seems a bit strange to write because I don't have an a sub n defined anywhere. So instead of writing that, I'm going to just write my limit of the natural log of n over n as n approaches infinity is going to be equal to 0. Now, what's really important to note here is that there is no magical wording. I don't have to write all these words in exactly this order to receive full credit. That's not the idea. When we write out an argument in mathematics, there are certainly better ways and worse ways to try to communicate an idea, but it's about communicating an idea first and foremost. So your job as you write up answers on worksheets or things in the notes or on assessments in class is for you to try to explain to me how you are thinking about the problem. Connect the dots for me. What is it that you're doing? You don't have to use all these words in exactly this order. But of course, if you want to communicate an idea, you do have to actually use some words. So I will always be requiring that when I ask you to write an argument here in Chapter 5, that you always write arguments using complete sentences. That means you're going to have things that look like a big mixture of mathematical symbols and regular English words. This takes a little bit of getting used to, but you'll see that in all the questions that we're going to go through together, I'm going to try to model this for you. And all the solutions to my worksheets will also have this same sort of modeled explanation.